students. So here in this session we shall discuss about the flow measuring devices. Okay, here in this flow measuring devices there are a lot of devices that can measure the flow, but here in this particular session we shall concentrate on Orifice meter, and that too here we shall see the treats of Orifice meter, and we shall derive an expression for the discharge through a Orifice meter. Again, this Orifice meter will come in the module number 3, okay, and chapter number 2. Sorry, here it is going to be chapter number 1 of module 3, that is fluid dynamics. Under the fluid dynamics we are studying the flow measuring device. In the flow measuring device, here in this session we shall look into the treats of Orifice meter, as well as we shall derive an expression for the discharge through an Orifice meter. Okay, so in the previous session we know there is one more device that can measure is Orifice venturimeter. Even venturimeter can be used as a device to measure the discharge. Okay, but Orifice meter is having a different approach in the measurement of discharge, but the fundamental of measurement, that is the law behind the measurement of Orifice meter, is also same that of the venturimeter, that is the Bernoulli's equation. Okay, both venturi and Orifice meters will work on the same principle of measurement, but how this is going to vary with respect to the venturimeter is we shall see. Okay, but before that, how it is defined is Orifice plate, even Orifice meter, or you can say it is a Orifice plate, is a device used for measuring flow rate, in which a restriction is created to achieve the pressure difference. So here what you have to do is you have to create a pressure difference. Okay, you have to create a pressure difference for the flow, so that you are going to get the value of the pressure difference. Using that pressure difference, I will substitute that value of pressure difference into the expressions, so that I will get what is the flow rate in the channel. Okay, so the fundamental is you have to restrict the flow rate, so that once you restrict, what will happen, there is a pressure difference. So how this is, even in the venturimeter also you are going to restrict the flow by reducing the cross section, right? Here also I'll make some arrangement so that there is a very less cross section is available for the flow. Okay, right? But the how I'll make sure there is a very less area is available for the flow is by inserting a plate. Okay, what I'll do here is, this is the pipe. Okay, this is the pipe. Okay, so in between the flanges of two pipes, okay, I'll insert a plate. Okay, so this plate will have some holes, right? This plate will have some holes, right? So this hole is going to be of half the diameter of the pipe, right? For example, if you have considered the pipe of say 10 centimeter, okay, the pipe is going the orifice is going to be of diameter, say half of it, say 5 to 2 to 3 to 5 centimeter, like that it goes. Okay, means here in the venturi, when you were discussing with the venturi, okay, the cross section was gradually decreased. Okay, then there comes a throat. Okay, again there is a gradual increase in the area of the flow. But here that I don't do, right? Here I'll just insert a plate, and that plate will have some area, very small area is available for the flow. This small area of the flow, make sure there is a restriction for the flow. This restriction creates the pressure difference, right? So this is all about the Orifice meter, how this is going to actually work in the flow, right? For the flow, right? Even you can say it's a hourglass, no? This is 1 hourglass, right? So sand will keep falling from top glass to bottom glass. There comes a small area for the flow, right? There comes a very small cross section of the flow. Even this throat or the very less area for the flow can also be thought of a orifice plate. This is for your understanding. You can imagine how the orifice can look like. Okay, right? So it is to put very simple words. Okay, for the flow, okay, right, when there is a flow in the pipe, you are going to insert a plate. Okay, right, but that plate will have very small cross sectional area for the flow. When there is a small cross sectional area is available for the flow, okay, that creates a restriction for the flow, that will ensures there is a pressure difference. This is how the orifice meter work in the reality. Okay, now what we'll do here is we shall derive an expression for rate of flow through a orifice meter. Okay, the construction part we shall see. This is a uniform cross section of the pipe. I have considered a uniform cross section of the pipe, and in the pipe, okay, at some point I'll insert a plate, right? I'll just insert a plate from top, right? So now imagine, right, this plate allows only this much of area is available for the flow, right? Only this amount of area is available for the flow, right? Now this is cross section 1. Okay, right, this is cross section 1 and this is cross section 2. What are the features of cross section 1 is the diameter of this cross section 1 is very high. Okay, and where I have the section 2 I have considered where the flow of the uh, fluid is very small. The cross section of the fluid is very small during the flow, right? So this is the section 1 and this is section 2. What is the feature of section 2? Here you will get very minor thin cross section of the flow, right? And this is the plate where I have inserted, and between cross section 1 and 2 I have connected a differential manometer. Okay, and when there is a pressure difference, this differential manometer gives a deflection. Okay, this deflection I will put into the calculation for the expression. I'll get the discharge value, right? This is how it works. Okay, now what are the things I assume is let P1, V1 and A1, right? That is P1 is a pressure, V1 is the velocity and A1 is the area at the section 1 here, and P2, V2, A2 be the pressure, velocity and area at the section 2, right? Section 2 is the cross section where you will be having very thin or very less area is available for the flow, right, of the flow, right? Very thin cross section of the flow. Okay, now again I will consider Bernoulli's equation between the section 1 and 2, right? Then I can write P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2, right? Now what I'll do, I'll keep P1 by rho g on the left hand side. I'll send this and I'll keep Z1 same. Okay, and I'll send this V1 square by 2g on the right hand side, and I will bring P2 by rho g and Z2 on the left hand side. If I bring like this, okay, this is how it looks like. So it looks like P1 by rho g plus Z1 minus P2 by rho g plus Z2 will be equal to V2 square by 2g minus V1 square by 2g. But we know that for a differential head, okay, H, right, will be equal to this value. The differential head or the pressure head can also be equal to what? P1 by rho g plus Z1 minus P2 by rho g plus Z2 will be equal to differential head h. So I know this term as h, so I'll replace this whole term by h. Okay, then I can write h is equal to the differential head h is equal to v2 square by 2g minus v1 square by 2g. So I will send this 2g common in the denominator. I'll send it to the left hand side. It becomes 2gh is equal to v2 square minus v1 square. So v2 square, I'll send this v1 square onto the left hand side. It becomes positive and it becomes v2 will be equal to, now it is not v2 square, v2 is equal to root of the term v1 square plus 2gh. I'll call this one as equation number 3. Okay, now a term that comes during this derivation is vena contracta. Vena contracta is the minimum cross section of the flow, right? Vena contracta is the minimum cross section of the flow, right? Where is the minimum cross section of the flow? That is nothing but the cross section 2. This is where I'll get a very thin cross section of the flow. Okay, right? So that becomes, so the significance of section 2 is nothing but where I'll get a vena contracta. Right. Now the section 2 is at vena contracta and A2 represents the area of the vena contracta. Okay. Now let AO, right? AO is the area of the orifice. Where AO comes here, right? This is AO, right? This is going to be, this area is available for the flow, right? Only this area is available. So that area I'll call this one as AO, right? So what is AO? AO is the area of the orifice. Now there comes one more term, that is coefficient of contraction, right? CC we call them as, right? So CC is nothing but coefficient of contracta. How it is defined? It is a ratio of area of the flow, right? It is a ratio of area of the flow jet divided by area of the orifice. So CC is equal to A2 by A1, right? But I want to know what is, I will equate it to A2. So A2 will be equal to CC into A0. So I will call this one as equation number 4. Now I know what is continuity equation. So that is nothing but if you apply for this equation section 1 and 2, it becomes A1 V1 is equal to A2 V2. Even I can equate it to V1. So V1 is will become A2 V2 divided by A1. Right. So V1 will be equal to, I know what is A2, right? A2 is nothing but from equation number 4, that is EC into A0. So CC into A0 into V2 by A1. I will call this one as equation number 5. Okay. Now I'll again consider equation number 3 that we have derived to equation derived for V2, right? So V2 is equal to root of V1 square plus 2gh. So V2 will be equal to root of, I'll just replace this V1 by this term that we have derived here, right? So V1, actually what is V1? That is CC into A0 into V2 divided by A1. So I'll just substitute in place of V1, I'll substitute this term plus 2gh. Okay, I'll just take this square, okay, in each term in the this ratio, then it becomes CC square into A0 square into V2 square divided by A1 square plus 2gh. Now I'll make a small separation. It is nothing but I can make A0 square and A1 square as a separate term, okay, and CC square into V2 square plus 2gh. Okay, this is equal to V2. If I equate it to V2 square, so this square root goes off, then it becomes A0 square by A1 square CC square V2 square plus 2gh. Okay, now what I'll do, I'll send this term onto the left hand side. So it becomes V2 square minus A0 square by A1 square CC square V2 square is equal to 2gh. Between these two terms, V2 square is common, so I'll just take it separate. So it becomes 1 minus A0 square by A1 square CC square into is equal to 2gh. Okay, again V2 square I'll keep on left hand side. I'll send this term onto the right hand side, so it becomes in the denominator. So V2 square is equal to 2gh divided by 1 minus A0 square by A1 square into Cc. Now if I equate it to V2, it becomes under the root. The whole term that is here will come under the root. So I'll call this one as equation number 6. Okay. Now we know what is discharge, right? Discharge can be equal to either it is A1 V1, can also be equal to A2 V2, because I know the value of A2 as well as V2 here. Okay, here I know the value of V2 and even I know the value of A2 from equation number 4 and equation number 6. I can make use of this discharge. So Q is equal to A2 V2. So what is A2? That is Cc into A0 into V2, right? So but from equation number 6 I can replace V2 by this term, right, that we have derived in the equation number 6. So that becomes Cc A0 into root of 2gh divided by 1 minus A0 square by A1 square into Cc square. Okay, right? What I'll do now, I will separate the root in the numerator and denominator, then I'll get a term like this. It becomes Q is equal to Cc A0 into root of 2gh divided by root of 1 minus A0 square by A1 square into Cc under the root. So I'll call this one as equation number 7. Okay. Now there comes one more parameter for the derivation, that is nothing but coefficient of discharge, because we could have stopped the derivation here itself. Okay, but the using the value of Cc is not so pronounced in the calculation, means it is not viable or it is not so effective in the calculation. So somehow I want to eliminate this Cc from the equation. Okay, in that process I want to include this Cd into the equation. So in the process I am defining the coefficient of discharge. Okay, so what is coefficient of discharge? It is a ratio of actual discharge through the orifice to the theoretical discharge. Okay, is known as coefficient of discharge, right? So mathematically coefficient of discharge, I'll just given as that is mathematically coefficient of discharge can be written as, so here I will get a relation between the coefficient of discharge and coefficient of contract like this, right? Coefficient of discharge and coefficient of contracta, contraction is going to be connected by this mathematical expression. Okay, so this is the expression that I have got in the equation number 7. Okay, here in this equation number 7, okay, I want to replace this Cc, right? So I know this is mathematical relation between Cc and Cd. So I want to replace Cc, I will equate it to Cc. So Cc will be equal to, so this denominator will come to the numerator. Okay, so it becomes Cc will be equal to Cd into root of 1 minus A0 by A1 square into Cc divided by the denominator remains as 1 minus A0 by A1 square. I will call this one as equation number 8. Okay, now I know what is equation number 7. Okay, this is equation number 7. Okay, in place of Cc, okay, I will substitute equation number 8, that is nothing but Cc in terms of Cd, right? So I'll just replace this Cc with the Cd and this term. Okay, so this is remain term, that is A0 into root of 2gh divided by this term in the numerator remains same. Okay, so because numerator and denominator has the same term, so that can be get cancelled. Then it becomes what are the terms remained after cancelling is Cd A0 into root of 2gh divided by root of 1 minus A0 by A1, that whole square. Okay, so I have written here, that is discharge Q will be equal to A0 Cd into root of 2gh divided by root of 1 minus A0 by A1 square. Okay, right, I'll take the LCM in the denominator under the root, then it becomes A0 A1 square minus A0 square by A1 Okay, so this in A1 square, if I make it to come to the, if I want to remove out of this root, this comes into the numerator. So I can ultimately write the expression for discharge for an orifice is equal to, Q is equal to CD, that is coefficient of discharge, into A naught. A naught is the area of the orifice, into A1. A1 is the area of the pipe, into root of 2gh, where h is the pressure, sorry, it is the differential head. Okay, right, this is the differential head. Okay, divided by root of a1 square minus a naught square. Okay, where CD is the coefficient of discharge for an orifice. One thing one should remember, the coefficient of discharge for the orifice meter is very small compared to the venturi meter, because for the venturi meter, in the derivation what we are doing, what we have done in the venturi meter, okay, there used to be a gradual decrease, right? There is a gradual decrease, and there comes a throat, and there is a gradual increase. So there will be no losses. The amount of losses because of this sudden contraction, because there is no sudden contraction, okay, so losses will be very less. But when it comes to orifice, there is a sudden gradual there is a sudden decrease in the area. So in that process, there is a loss of energy, right? There is a loss of energy during the flow, right? So that creates a low coefficient of discharge for the orifice meter, right? So this is about the derivation of expression of an orifice to determine the discharge, right? Thank you for joining in.